Good morning, everybody. Thank you for attending my webinar this morning. It's very early July. Nice to start the back half of the year, taking a step back, seeing how we can find some cost savings, especially in times like these with coronavirus, which is still in full swing. But all things considered, thank you everyone for taking some time out of your day to attend the webinar. I hope you guys find some value out of it, and hopefully it'll change your philosophy on how we approach design. And so today we're going to be looking at how we can take the tedium out of system design iterations using the ANS module. But before we get too far into it, let me introduce myself. My name is Nick Vastine. I'm a business applications engineer with Applied Flow Technology. Anytime you have questions about capabilities, licensing, pricing, anything like that, that's usually right up my alley. So maybe I've spoken to a few of you already, but if not, it's nice to meet you. And again, thank you for spending this time with me today. So with introductions all out of the way, let's get into kind of the meat of the presentation and take a look at our agenda. So today, the first thing I want to talk about is some of the problems that I see facing engineering design. Because engineering is a business, a lot of it comes down to being on time and on budget. We'll see how some of those boundaries and limitations can hinder the design process and make it a little bit more difficult to find some marginal returns where it's pretty evident there are some. We'll take a look at pipe size specifically, how that is under considered during the design process with kind of an explanation why that is. Again, coming back to some of the problems facing engineering design. If we do consider pipe size as a variable we want to look at, we can see how we would determine what an optimal combination of pipes is. We'll see how the automated network sizing module, or the ANS module, can find that optimal combination. We'll see how it works, how the definitions that go into it are pretty intuitive and already exist for your system, before we jump into an example. And so we'll work through a pretty rudimentary example where we'll design different things like design requirements and candidate sets, and all of this will be clear as we work through kind of an introductory theory to what the ANS module is doing. Finally, we'll look at how we can expand the ANS module's capabilities. So beyond this kind of rudimentary example, that'll take just minutes to set up, and we can reap immediate benefits on our system. We'll see how we can incorporate things like cost information and designing for different operating scenarios within the same design. So that's our agenda laid out. Let's take a look at some of the problems that we see facing engineering design. So as I mentioned, one of the most important things that comes up when you're designing for an engineering system is making sure your design is coming in on time. Because engineering is a business, a lot of it is pushing projects forward, how you're allocating your resources. If one project gets delayed, now you have to look at those resources are now tied with that, and they can't be doing something else. So there's always trade-offs. It's always important to push designs forward, meet deadlines, even if it's spending time on the weekends or anything else. With engineers specifically, engineering is kind of a fruitful job. It's one of the appeals of being an engineer. And so engineering time is expensive. And so pushing projects forward, making sure they're not following delays, that's also saving the company money, but also ensuring that your design is being created on budget. So looking at your design, if you have $1 million budget, it's hard to justify going over that. Generally, you want to come in under, and that'll make it look better on yourself. And so meeting these two criteria of being on time and being on budget are two of the most important facets of engineering design. But above all is creating a design that's going to work. So you can take a simple design, quote it at $25 to build it, and spend 2 hours on it. But if your design never works and it can't be implemented, then all of that work was essentially for nothing. So first and foremost, above all, your design has to ensure that it works. So how do you define whether or not a design works or doesn't work? So this is where we can introduce the idea of a design requirement, or a specification that a design has to meet to work for the client or work for your business. And so some examples of design requirements, they can be flow rate specifications if you need a specific flow. Delivery pressure, if you're looking at, for example, a residential system where it needs to be supplied at this pressure, or like a gas pipeline. You can also look at things like maximum velocity, where sound might be a consideration, erosion of the pipes itself. You can't exceed this velocity or else the design may deteriorate faster than you're anticipating. But all these design requirements are pretty natural and really outline where your design needs to fit within. And so now we can take a look and say, what has a significant impact on all of these different requirements? Sure, we can say pumps and components, losses through things, scaling, all these other factors, but the foundation to all these designs comes down to pipe size. So if we look at a very basic example, let's look at a small permeation between different pipe sizes. If we have a very small pipe and we make it larger, we will, for example, look at this velocity. So by expanding that diameter, you're increasing the cross-sectional area. The velocity through it is going to decrease, potentially meeting that maximum velocity specification. Through a larger pipe, you're also going to see much less significant pressure drop. So that can help with your delivery pressure. And if you have less pressure drop, maybe that can improve your flow rate. However, by increasing your pipe size, you're going to see an increase in cost. So if we look on the flip side and now we try to shrink our pipe size smaller and smaller, how is that going to impact our design requirements? So it's going to reduce our delivery pressure because you're going to see more losses through it. You're going to get a higher velocity. It can impact the flow rate. And if we look at it more as a pump and system interaction, a smaller pipe is going to require a much larger pump. And so you're going to see additional costs there, even if you're saving money up front by purchasing a much smaller pipe. So there's some intermediate between the two that is really a cost minimum. And so all of these come down to cost benefit analysis. If the pipe is slightly bigger, you get these cost savings and cost additions. Same way if the pipe is smaller, but between there is some Goldilocks area. And so that's what we're going to be chasing. But why don't engineers consider pipe size as thoroughly as one would think, especially if it has this much impact on a system? Glad you asked. So if we look at engineering design as a pyramid, we have a foundational piece and then we can build upon that system. And that foundation is usually your pipe diameters. So once you create those pipe diameters so that it's meeting your basic system requirements or design requirements, then you can begin sizing your pumps and looking at different components, pulling specific data from data sheets, for example, to make your model as accurate as possible. And those things are kind of interrelated where you can get a slightly larger pump or a slightly smaller pump if you have less pressure drop across a control valve, for example, or if you're operating close to BDP. But once you reach this phase of looking at components and doing pump sizing, rarely are you going to take a look at these pipe diameters. So you get pipe diameters as close as you can, hope that you don't run into an issue as you continue through the design process. And so by fixing these pipe diameters, that's where it's not really considered because all of these changes down at the foundational level are going to have an impact on this additional engineering work. And so because all of this takes time, time is money, it's more expensive to try to perturb these pipe diameters and make small adjustments to see if there's marginal savings. So let's say I've convinced you that pipe sizing is a bit more valuable and maybe we should look into it a bit more for our upcoming designs where we're not in that pump sizing and component sizing phase. How difficult would it be to do pipe sizing by hand? So let's do a theoretical example with a very simple system, looking at a single pipe into and out of a pipe between two different reservoirs. So in Fathom, it would look something like this. And with pipe sizing, what we want is specific pipes that we can purchase. So we only want pipes within a specific range. We don't want a numerical pipe that is 3.34 inches in diameter because you're not going to make any savings by having that specifically manufactured. Instead, we want to pull from a catalog of different pipe sizes. In this case, we'll call that a candidate set. So we want different potential pipe diameters we want to consider for this specific system. In our case, since we're doing a theoretical example and it's very general, we'll make a pretty wide candidate set, and we'll look at everything from 1/8 of an inch in diameter all the way up to 18 inches. This is actually truncated a little bit. This is based on ANSI steel inch pipe diameters, which can go all the way up to 48 inches, I believe. And so we're truncating it quite a bit just to serve as an example. So we have our entire candidate set where these two pipes can be 1/8 of an inch, 18 inches, 12 inches, 4 inches, really anything within this candidate set that we've defined. So if we break it down, each of these pipes will have 21 different options based on the candidate set we've selected. If we do sensitivity analysis where we're changing one pipe, keeping one fixed, and looking at every possible combination, we have 441 combinations to consider. So imagine in Fathom if you had 441 combinations in your different scenarios and you're trying to find which is going to balance out and which will meet your design requirements best. And odds are your piping system isn't just two pipes as simple as this. So what if we look at something a little bit more complex, where now we have a 4-pipe system, we have a pump inlet, a pump outlet, and then we have a branch to 2 different reservoirs. Off the cuff, you may think that the combinations are going to more than double, so you'd see at least 1,000 combinations. But with these interacting variables, it escalates exponentially. So rather than the 400 combinations we had to consider before, now we have 194,000 combinations. Now you could argue that some things may be unreasonable. Why would you have 1/8 of an inch pipe going into an 18-inch pipe? And so there you can truncate your candidate set even further. But as long as your number of pipes continues to increase, you're still going to see that exponential growth far outside what is reasonable for an engineer to spend time on to reap those marginal savings, which is a lot of the reason why a lot of engineers will figure out their pipe sizes, find one option that'll work, and move forward with the rest of the design process, again, to stay on time and to stay on budget. So if we extrapolate this idea, going from 2 pipes to 4 pipes and see how it expands, we can see our total combinations for a 21 option pipe size range, or the candidate set that we have over here. We can see by 5 pipes in our system, we're already above 1 million different combinations, 6 going into the tens of millions. And if you looked at your own system with 30 or 50 pipes, you can imagine that's going into the billions and trillions of different combinations. And so root sensitivity analysis to find a cost minimum isn't the best option. So the question then becomes, how do we bring this number down? How do we make it more reasonable rather than testing every potential combination? So how do we reduce the number of possible combinations? One is an option I already brought up where we can reduce this candidate set. So for example, if we know the flow rate is going through the pump, and we know it can't beat a specific velocity, we can do a simple hand calculation and reduce this number of candidate sets. So we can start at 3 inches, for example, and that'll knock off quite a few of the 21 options. Another alternative is to look at the system itself and try to draw conclusions. So if we go back to our example, let's say that the pump inlet and the pump outlet should be the same size pipe. So if we link these two, we can create what's called a common size group. And now, instead of 21 times 21 options or 441 combinations between these alone, we've reduced it to a single pipe. Similarly, with this discharge, if we say that pipe 3 and pipe 4 are going to be the same size, now our number of variables has been cut in half. So rather than the 194,000 combinations to consider, we're back down to this 441 combinations. So by combining these pipes together, making the logical assumption that flow in and flow out are going to be the same, so your pipe diameters are likely to be the same, then we can reduce the number of potential combinations. And in the context of the ANS module, that'll also help with runtime significantly. So how do we reduce the number of possible combinations is truncate our candidate set, though savings are much more marginal there, or look for areas in our model where we can make pipe combinations and create common size groups so that the number of variables down here is reduced. So let's say now we're evaluating the different options as we're plugging in these different pipe sizes. How do we compare these different options to find which is better? The first distinction you want to make is the difference between a feasible and an infeasible design. Really, you only want to consider those designs that are going to meet your design requirements because, again, first and foremost, that's our entire goal of design. But if we have a range of feasible designs, then we can start comparing them to find which among those fewer options are best for our system and are going to minimize things like a system cost. So this is where you involve something like a sizing objective, or what metric we want to use to compare different design alternatives. In essence, we have to think of this as a computer. So we have to create something objective, something numerical that the computer can compare so that while it's running these different combinations, it knows one, which direction to work in, and two, if it's found a minimum that'll meet your design requirements. So some different sizing objectives we can look at is pipe weight, for example. This is the most simple sizing objective because a lot of it is already built into Fathom. Whether it is looking at different pipe diameters or you want to consider something like the weight of the fluid, that can all be considered without much additional work, and that'll be the example that we're going to work today. Taking a preview at some of the extended capabilities of the ANS module, you can look at things like capital cost. So if you know the price per foot of a pipe, you can consider capital cost instead. There you can incorporate things like pump and component costs as well. So if you want to minimize the upfront cost of your system, if you're designing for a client and trying to underbid a competitor, you can size for that objective. Alternatively, you can look at life cycle costs, where now you're considering not only the upfront investment, but you look at the life of the system. Let's say it's 25 years, and you can explore the recurring costs that'll come up over those 25 years. This again comes back to the example, if we make a pipe slightly bigger, maybe our pump can run with less energy. We can recuperate the cost of the larger upfront pipe by reaping those savings on the energy back end. So in this case, let's do an example. Let's look at capital cost as our sizing objective. So in general, you can imagine a larger pipe has more material, and so as such, as the pipe grows, it will increase in cost. Now you could argue things like maintenance or installation can sway these, and those can also be considered in the ANS module. But for our simple example, let's say pipe cost increases with pipe diameter. We can also take a look at our pump cost. So as the pipe gets very, very small, we're overcoming those larger and larger pressure drops. Whereas when our pipe is very large, there's pretty negligible pressure drop, and so our pump costs reduce. If we sum these two together, we can see that there's a natural value within this total cost. And we can call that our system cost minimum. So now if you're a computer and you're looking at this total cost, you can start at 30 inches in diameter, for example, move up to 32 inches, see there was an increase, and then move the other direction as you're trying to approach this minimum. In the same way, if you start at 10 inches and you move to 9 inches, you can see there's maybe a more steep increase in cost, and so maybe you make a bigger leap in the opposite direction. So this is something that would take a lot of thought from an engineer, and with a lot of thought comes a lot of time. But for a computer, you can do thousands of comparisons per second as you approach this system cost minimum. So again, it's how are we phrasing the problem so that a computer can understand it and do all of the tedious iterations and comparison to find this system cost minimum. So that brings us to the computer, which is the automated network sizing module. excuse me. And so being built upon the hydraulic solver of the AFT Fathom, or for compressible flow, AFT Aero, it can base all of its testing by running that solver and do all of its little permutations in pipe diameter through the module itself. And so the ANS module will take your initial design and it'll vary different pipe sizes based on that candidate set. So it's taking all those individual pipes, plugging them in, seeing if it'll be feasible and meet those design requirements, and the set that it's pulling from is that candidate set. So whether it's meeting those design requirements or not, is that infeasible or feasible? If it's determined to be feasible, now it's trying to approach that design objective. And so with these very large systems, we can use intelligent searching to try to navigate the millions, if not billions and trillions of different potential pipe size combinations so that you're not doing root sensitivity and trying to find a needle in a haystack. The other thing is it's sizing the system holistically. So if a pipe is slightly larger on one end, maybe these other pipes can be slightly smaller. Again, trying to juggle this cost-benefit analysis for you by looking at the system as a whole. As it's doing that juggling, it can also do cost analysis. So if you wanted to build out something like a cost database for all of your different pipes, diameters, and different components or pumps, then you can do comparison looking at minimizing initial investment or minimizing something like life cycle cost. So if you had a client looking to minimize cost upfront and that was the only concern, you could size your system to minimize that initial investment or to minimize that capital cost. But since you already have all of that input in, you can also try running to minimize the capital and recurring costs. That way, it's much easier to justify to a client that, well, if you give me an additional $200,000, we can save you $500,000 on the overall system over the life of the system. Additionally, it can take into consideration things like the time value of money, but to not get ahead of myself, we'll talk about that a bit more towards the end, looking at some of the extended capabilities. Another thing with the ANS module is we can look at some different operating conditions. So not all systems are going to be operating in one steady state all the time. So there has to be some flexibility there. So you can size one single system that will meet all of those different design requirements. One common example that we use is a residential water system, where not only does it need to meet the day-to-day flow rate requirements for all the households, but it also needs to meet peak demand during something like a fire. And so ensuring that both of those design requirements are met in all the cases, that's just removing an additional step of building an initial system for one situation, testing it against a second situation, and doing that check back and forth. It's easier to just size it once, know that you're going to meet those design requirements in all your different cases, then move forward with all of your different engineering design. So now we can see it in action. Enough talk, let's get into the software and see what we can do. And so the system that we're going to be looking at, or the system that we're going to be sizing today, is a heating loop system. And so all of these pumps down in the left, these are all going to be sized. And so we don't have pump curve information for them, but if we did, we could input that and still do the same sizing. Similarly, with these flow control valves, these are all being sized. And so all of this is in the introductory level. We just know the lengths that we need to meet. And we're going to let the ANS module determine the pipe diameters. And so the easiest way to do that is by specifying all of these pipes as 16 inches. So rather than trying to spend the time and mess around with the pipes to get it close, we can let the ANS module take it from here after we just assume a single pipe size. What's interesting about this system is there's also going to be an expansion later on. And so because this is a brand new system, we can size the entire system at the beginning even though we don't have this expansion during that initial construction. And so that'll ensure that later on, we can still meet these flow requirements without breaking a maximum velocity through these pipes, for example. So by planning and having some foresight, we can take further advantage of the ANS module to size the expansion while we're sizing that initial system. So now we can take a look at the software. And here we have our standard model. It's just a basic Fathom model where we still have our scenarios, we still have our toolbox. If we wanted to run it and get output, we can still do that. So let's actually try that and see what happens. The reference pressure issue. So this may be something that you see in a similar situation where you're doing pump sizing and you're throwing these flow control valves where now you need a reference pressure downstream of these pumps and upstream of all of these different flow control valves. So let's talk about why this occurs first. So the way that I like to explain it is these pumps are currently in sizing. All we know is they need to output this fixed flow rate. This upstream pressure of the pump is informed by this tank, and the amount of pressure it has to add is dependent on this flow rate that we're specifying. Similarly, if we look at these flow control valves, we can see they have a 1400 gallon per minute specification. The downstream pressure is informed by this tank, and this upstream pressure is kind of nebulous. This upstream pressure is defined by this downstream pressure of the pump, and because it can add as much pressure as it wants, this flow control valve can remove as much pressure as it wants. There isn't really a unique solution. And we actually have a full example dedicated to just this reference pressure issue where you're doing pump sizing with a flow control valve, why you need to define this internal section a bit differently so that you can do the sizing as you want. In our case, we're going to do the short version. Instead of having flow control valves on each end, we're going to change this to a constant pressure drop. And so we're going to use this constant pressure drop as kind of our minimum pressure for controllability. And what that does is now we have this pressure, we can back it up, say 10 PSI fixed across this valve, and now this entire section has some point of reference pressure. You can also do that for this flow control valve, where we're just setting to 10 PSID. Now, if we want to do a run, calculations complete. Take a look at our output, no problem. So any standard model can be used with the ANS module. Generally, new designs are better, or if you're doing something like an expansion where you're doing new design, because it's easier to just draw out the system and let the ANS module start from scratch so that you're reaping all those time benefits. So we have our base model that we're going to start with. Now we have to turn on the ANS module. And so there's two ways that we can do that. First is down here under add-on modules, where it lists GSC, XDS, SSL, and ANS. Or we can go up to tools, activate modules, and click ANS. Now we can hit OK. So now, after activating the module, we can see that we have a new tab. So we have our 5 traditional windows, and now we have a new sizing window. If we go into that, we can see down here is the sizing navigation panel, where we have our sizing objective, some sizing assignments, which we haven't talked about, but are pretty intuitive, candidate sets, which we've talked about, design requirements, and then finally our sizing method. And so there's a lot of different parts that go into the sizing tab or window, and we'll go through it here as a pretty simple example. The first point to show is these 3 buttons up here. So you can either perform sizing or let the ANS module work as intended. But if you're done with your sizing and you want to just run analysis and do your different scenarios, you can do not size. And now it's back to just a standard Fathom model. We can see a lot of our input has been limited. It'll actually leave our design requirements and they'll act as design alerts. So if it's ever not met or exceeded or the design requirement is broken, it'll show as a warning within our output. We can also calculate weight, but not size it. So this is good if we just want to determine the cost of a system, what's the overall pipe weight. This can be a quick and easy way. Again, doing a standard run with this additional cost analysis. In our case, we're going to be performing the sizing today. And here is our objective. So again, this is what the computer is going to be using as it's comparing these different feasible options to approach that minimum system cost minimum we've talked about. So here we have pipe weight. We can minimize it. We can also maximize it if we wanted to. Can't think of many cases where you'd want to maximize it. So we have included a note to make sure. Here we're going to minimize, and there's some other considerations such as flow volume, surface area if you need to coat the pipes, and pipe and fluid weight, for example. The next most interesting one, I think, or really pushing ANS to its full capability, is looking at this monetary cost piece. So here we can see where we want to size for initial cost. We can account for things like material and installation, but disregard these recurring costs. We can size for the initial cost, but take a look at the energy costs. So this is good if we want to compare this option with the next option, which is trying to minimize the entire cost of the system over the system lifetime. So here, once you begin accounting for recurring cost, you should be accounting for things like the time value of money. So you're getting to a net present value, or in this case, a net present cost. So you could specify the system life as 25 years, determine your interest rate, likely internal to your company, as well as an inflation rate. Then you can also specify energy cost or inform energy cost databases, and all of these are pretty customizable. In this case, we're going to be looking at pipe weight because we don't have to look at the upfront example or upfront investment of building out something like a cost database. And pipe weight is going to be pretty close to that sizing for initial cost because those smaller pipes are going to weigh less, and because they weigh less, it's going to cost less. And we'll take a look at some different ways that we can try to account for the occurring costs or recurring costs like energy by implementing some different design requirements. So here's our sizing objective. We're shooting to minimize this pipe weight, and that's the computer's path. The next thing to look at is sizing assignments. So sizing assignments is pretty intuitive. Which of these pipes do I want to be sized? If, for example, we were only looking at this expansion, maybe we don't want to rip out these pipes and replace them just to account for this new flow path. So what we can do is select our expansion, go to sizing, say workspace. Now they're all selected here, and I want to include that in the sizing. In our case, we're going to be looking at everything, and we want to always include that in the weight. Again, because this is just an initial system, and I want to size every part of it, every single pipe. Great. There's also some options such as include in weight if the size changes. So that might be good if you want to see how good your existing design is. So let's say we were looking at this expansion again, and all of these original pipes were set to include in weight if size changes. That means that only if this pipe diameter is calculated that it should change, will it be included in that system cost. And so if you are looking at monetary cost, again, for example, then it'll say it'll cost this much more to change this pipe, and it'll factor it in kind of into the cost benefit analysis to say, well, we can get by with the existing pipe, or if we increase it in size, then we'll be much better off and actually save more money. So again, finding that minimum, looking at cost benefit trade-offs. In our case, always include in all of them because we want to size everything. The next piece is over here, and so these are where our common size groups are going to come in. So if you remember, rather than having 3 different pipes that we're going to be sizing independently, especially into and out of the heat exchanger, you would expect those pipes to be very similar, or the pipe diameters to be the exact same. So what we can do with that is create that common size group. That'll reduce the total number of independent pipe sizes that we have to consider. So to do that, we can highlight it. For example, we'll do pump A. We can add pipes to a common size group, and we can say pump A. And so by investing a bunch of energy up front, by creating different common size groups, what we can do is drastically reduce our runtime. Again, it comes back to that exponential growth, where instead of trying to reduce our candidate set, since that kind of marginally reduces it because it's not checking extremes as often, creating common size groups can definitely help there. It'll also make purchasing a lot easier for your purchasing department, rather than having a bunch of different unique pipe sizes. We can just size all these pipes at the same time and say, well, I need 18 inches diameter, this amount of feet, rather than 18 inches, 16 inches, 18 inches. So there's a lot of different intuitive benefits there. So I'll add heat exchanger D. And then one more to add is just going to be this main header line. And we could also, if we wanted to, go above and beyond and create a common size group between these two. But in our case, for example, I think we've created enough. So looking at this system, it's kind of hard to tell where we've drawn our different common size groups. So the easiest way that we can see it is going up to View, color our common size groups. And if we want to look at a very specific one, we can do that, where they'll highlight as we add them, or we can view all of our common size groups. So here it's very clear to see at a glance where the different common size groups are. And if we go to our sizing pane, now we can see our different groups here, where we can organize them by the group as well. So if I know pipe 2, 3, 4, I can see 2, 3, 4, again, the same pipes. So we can see they're all checked, they're all specified. Now we have 15 independent pipe size groups rather than the 35 that we would have started with. So again, now we've cut the pipe sizes in more than half. Rather than reducing the number of possible combinations by half, that exponential decay goes the same way. And now we have far fewer potential combinations to consider. The next step is looking at candidate sets. So now as it's doing its sizing, where is it pulling these different pipe sizes from? It's going to be this candidate set. In our case, we're doing a very intro sizing. And so I want to consider the widest range possible. So we'll just build out a ANSI steel with standard gauge, which we can select already built out for us. So if I wanted to be more specific, I could look at 1-inch increments. But again, in our case, I want to consider the full range. And here, if we know the flow rates going through it, we can look at that maximum velocity and maybe say everything below 3 inches we don't need, and everything above 30 we won't need, and that'll help reduce the number of possible combinations. But again, because it's doing intelligent searching and it's kind of weaving its way towards that minimum, truncating this area is not as helpful. In essence, if it looked at 1/8 of an inch and found very high cost, then it might jump to 4 inches and a very limited time go back to here. And so by that solution method, it's a bit easier for the computer to reduce the candidate set itself rather than having us reduce it. So we have our ANSI steel, we can say okay. And now we can assign all of them to our candidate set that we've created. If, for example, we were looking at the other side of these heat exchangers, where we link the two heat exchangers, and let's say we had a copper system going through the other side. Well, we can also size that same system in the same sizing pass by creating a secondary candidate set of copper, where we can add these all over and move it over based on which common size group it's in, or moving individual pipes over. So there's flexibility there by defining this candidate set. So here we've earned our green check mark. We can work our way through with our sizing objective, how the computer's comparing, our sizing assignment, where all of our pipes are being sized because it's an initial design. We have our common size groups to help reduce this number of independent pipe sizes. And it's going to be pulling pipes from our candidate set, which we've specified here. Now is kind of the bread and butter and where the most engineering thinking goes in, and that's in defining these different design requirements. And so again, how is our system, how do we know our system's going to work, and what is really the criteria for whether a system works or not? That's where these design requirements come in. So we're going to add a few. We can create a new design requirement. In this case, we're going to have a minimum flow through heat exchangers A and B. And here's some different parameters that we can specify with the ANS module. So if, for example, we want to look at hydraulic grade line, so if your design needs to account for things like overcoming elevation change in addition to overcoming pressure changes, hydraulic grade line may be a good option. We can also look at things like margin above vapor pressure if you have a NPSH requirement, or if you're pumping something very volatile like methane. We can also take a look at the pressure drop across it, as well as specifying pressure at a point where it has to meet this delivery pressure, for example. In our case, we're going to be looking at volumetric flow rate, where we need a minimum of 1,400 gallons per minute. And here we're going to specify that for heat exchanger A and heat exchanger B. And then we're also going to create a minimum flow for our other heat exchangers for C and D. Again, specify volumetric flow, set a minimum, and we have a 1,300 gallon per minute flow. So the next pipe design requirement is going to help with those energy costs. So if we ran the solver now, after we apply these design requirements, the computer is just trying to minimize this pipe weight. If you think about it, the easiest way to minimize pipe weight is to look at our candidate set. Say an 1/8 inch steel pipe weighs less than a 1/4 inch and everything else increases. So let's try an 1/8 of an inch all the way across. Sure, we can get the flow rate because remember these pumps are in sizing, so they can add as much pressure as they want. These flow control valves can remove as much pressure as they want, so we can pump as much liquid through here as we want, even if it's an 1/8 of an inch in diameter. So to avoid that, we can add a maximum velocity, and that's going to keep these pumps in check to make sure they're not adding so much pressure that it's ridiculous, and also help avoid that erosion as we've mentioned. So that'll make sure our answer is reasonable rather than just looking at, the smallest possible pipe size. And with the ANS module, similar to Fathom, how you can iterate and explore different options, that's just a scenario you can run. And so even if you don't include a minimum velocity or a maximum velocity, you'll find out pretty soon that your results may be a bit skewed. And so here we're going to apply this max velocity to all of them, and then we'll go up and define it as a maximum velocity of 10 feet per second. So here's all of our pipe design requirements. You can also look at different pump requirements. In this case, we're going to also add a control valve requirement. So here we're going to add a minimum pressure drop, and that's the pressure drop across the different valves. So we're going to look at a stagnation pressure drop. We want at minimum 10 psit. Again, similar to the other control valves where we set that as our minimum pressure drop for controllability. We're going to apply that to the control valves, which are still flow control valves. So now we're kind of double defining those valves where they need to have this pressure drop and at least this flow rate through them so that we know they're going to be controlling. So now we've earned our green check mark on our design requirement. We have all of our green check marks. Our status light is green with all of our sizing input corrected. If we wanted to, we could do our first run, but before that, we're going to take a look at our sizing method. So here, the first distinction to make is this sizing type. So continuous sizing just means that it's going to find the numerical minimum of this piping system. So if this pipe needs to be 7.67 inches in diameter, that's the lowest cost that we can get it to. That's what continuous sizing would tell you. In this case, we're going to use discrete sizing because I want something that our purchasing department can actually use. I want to tell them I need an 8-inch ANSI steel pipe rather than a custom-made 7.67-inch pipe. In our case, we're going to do discrete sizing, and we're going to look at the genetic algorithm. We're going to do that because I want to start with this continuous method. Again, because how we drew it up, we just have 16-inch pipe that we've assumed across all of these different pipes. If we start with the continuous method, it'll do that run. That'll say this is 7.67 inches, and we can use that as our new starting point for the subsequent iterations. And so it'll be much closer when we start discrete sizing than just starting discrete from the bat. So we're going to go genetic algorithm and start with this continuous method of our modified method of feasible directions. So all these searching methods, these are all kind of proven, and a lot are used in automobile manufacturing for things like aerodynamics, where you're looking at marginal return and trying to balance all these different things, especially if you're doing like Formula One racing, where every weight element is an additional cost to you. And so a lot of these are kind of built from the ground up to find those minimums. So now everything is set. We have our discrete sizing, so we know we're going to get real pipe sizes, and we can start our run. And so here we can see our cost of initial design is 321,000 pounds. This is kind of an arbitrary number in our case because the 16-inch pipe size was chosen arbitrarily. So if we wanted to, we could start with 48-inch pipe size for all of them. Then when we look at our final comparison, we can say, oh, well, we saved 90% off our initial design, even though you're skewing the numbers intentionally. So what we see here is our continuous cost was 216. So again, a pretty good improvement. But this continuous cost is the best possible cost in general. And so because it has that fine resolution where any pipe can be any size, this is kind of the perfectly optimized solution. It doesn't have to fit within the constraints of picking different pipe sizes that you can purchase. We can see up here the current cost of the system. It's checking for feasibility, so we haven't found a feasible cost yet, so it hasn't found a combination. But it's running through, thousands of iterations among the trillions of options that it could be running through to try to find this best feasible option. And so this is built on the back of the Fathom solver. And so it's running all these different iterations. Again, if you had to do this in Excel, it would be almost impossible, or to do it even in Fathom alone, where you're trying to manage all of these in different scenarios, it's going to be hard to balance these 1,500 scenarios. And so in the time that we've had this talk, let's say about 20 minutes of input, about 2 minutes in runtime, we can find a much better design rather than sitting at our desk trying to manually iterate all of these different pipe sizes so that we're at minimum meeting our design requirements. And so in 2 minutes flat across 2,000 different possible combinations, we have our discrete sizing calculations. Now we can take a look at our output. So here we can take a look at this sizing tab, which is specific to the ANS module, since now we're comparing before and after. And this is convenient because our starting point is all 16 inches. So any deviation from that is pretty clear to see in our output. So we can see some pipes increased, some pipes decreased, which means they were initially oversized, some even down to 8 inches and up to 18 inches for these main header lines. And so with that, again, it's juggling all these different things. How do you make sure that you're meeting your design requirements, which you can actually see here. So if we scroll down, you'll see that some are highlighted yellow. That's generally the design requirements that are guiding the design. So through 28, pipes 28 through 32, we see the highest maximum velocity that we've seen in this column, because that pipe is what's really governing that maximum velocity. Similarly, with these flow rates, we can see that these are closest to the minimum. The reason these are exactly 1300 is because of that flow control valve. It's just setting that flow rate. And similarly, up here, we can see that 1400. You can also look at our control valve design requirements, where we have our pressure drop of at least 10 PSI across the valves. And so now let's say we're done with our run and we want to transfer these results over. Similar to the GSC module, if you have any experience with that, we can transfer results to initial guesses and we can transfer these calculated pipe sizes. Then if we wanted to do sizing, say do not size, and run our model, we can see now our runtime is far less than 2 minutes. And we can also see in our workspace that now it's updated with these new pipe sizes. So some lines, like the header lines, have increased to 18. These are all fitting the same 8-inch pipe as well as the same 10-inch pipe. And we also see some natural common size groups where this 12-inch pipe and this 12-inch pipe are similar. So this could have been an area where we could have improved our runtime by making another common size group. Similarly across here. But all in all, not too bad for additional input, especially if you're doing these initial designs. And so that's the ANS module. Here's the sizing tab. It walks you through it pretty easily. Again, going from the sizing objective, which the computer is using to compare designs, the sizing assignments, which is which pipes are we sizing, candidate sets, or where we're pulling pipes from, or which pipes we're plugging into our design, how we know if our design is feasible or not, if it's meeting those design requirements, and finally, how we're approaching that system cost minimum. One other thing, and this would be much more elaborate in the cost situations, is if we calculate weight but do not size. So now I just want to see what the system weighs. We can go to output and we can take a look at our cost report. And so now we have our total pipe weight and we can see which parts are most significant. So if you wanted to adjust your design requirements to maybe adjust where areas of super high cost are, then you can make those adjustments, run it again, and do kind of easier iterations rather than just wasting time trying to see which pipes make your design work. So it's kind of expanding that analysis so that it's more fruitful rather than trying to make a design that works. So that's everything I wanted to show in software. We have a few more points in the PowerPoint. And so a lot of these I alluded to a bit earlier with the ANS module. The first is looking at your system for cost. So there's a few different ways that this can be incorporated, whether that's developing a component and cost database. So if you have frequent valves that you like to use or specific pumps that you have an agreement with the manufacturer, you can build those out and plug those into the ANS module as well. And also looking at pipes in general. So if you have pipe diameter, dollar per foot of pipe, including installation, maintenance, material, all of that can be built out. And that way the solver can pull from that information to find that system cost minimum. We also have things like scale tables. So if you only have a information for a 1-inch valve and a 4-inch valve, it can extrapolate between the two. Again, because we're looking for marginal returns and we're trying to find the minimum within a system or within an interaction of variables, by extrapolating, you can still approach that cost minimum because the costs are still going to be proportional. You can also factor in things like material installation and maintenance. So that's kind of discussing those pipe sizes as you're building a database out. And you can also use time value of money to back up things, especially when you're looking at recurring costs, so that all of your different design alternatives are on the same footing. You can also size for multiple modes of operation using dependent design cases. This is actually something we have an entire blog on if you want to build on your knowledge and kind of get more elaborate with the ANS module. So if I wanted to look at the expansion, I could alternatively have an initial design and then the expansion as a secondary design if those have different design requirements, rather than sizing them all at the same time how we did today. So that first example is anticipating future demand if you're looking at an expansion, or you can account for multiple operating scenarios, again calling back to the residential area and the firemen both having different design requirements which have to be met, though not at the same time. So if you found a lot of value, or you're starting to consider pipe size as something you think you should look at, we have a lot of additional resources. So we have a collection of blogs. One is from our president and founder, Trey Walters, who talks about how the ANS module has been brought from some of our previous products like AFT Titan and AFT Mercury to work with our core products like AFT Fathom and Aero, so that you can reap these sizing benefits to minimize your system costs. We have a collection or a couple of articles from Stephanie on the stack team or the support team, talking about what the ANS module is asking for. So this will talk about things like the objective and candidate sets and design requirements. Hopefully you guys are all experts by now, and how you can size up different options. And I have a blog about dependent design cases, or how you can create one design that meets all these different design requirements all in one run. I also wrote a white paper called 5 Issues Automated Network Sizing Will Solve for the Time-Deficient Engineer. And so this kind of breaks it down more on a manager level of some of the appeal that pipe sizing has, in addition to weighing all those cost-benefit analysis. So with that, there's the summary, but before that, let's actually take a look at our website, just so I can point you to some additional resources. So if we go to aft.com, we can look at our beautiful new homepage. And here we can click on automated network sizing. Where here you can read up a bit more on some more information. We have data sheets. If you need a quote, you can reach out to us. You'll probably be working with me on that. And if you want all those resources I've talked about in one central location, you can go to this blogs and videos, where we have some different blogs up, as well as those tech papers, or some tech papers proving the ANS module within context of a real system, as well as that white paper that I mentioned. We also have some overview videos, which are, very short, which give you the rundown, outlining what it's asking for, design objectives, candidate sets, requirements, and that kind of thing. We also have some previous webinars that you can take a look at, some which are Aero specific. So that's about all the resources I have. Now let's take a look at this summary. And so what is the ANS module for? Well, for engineers, it's hard to be on time, on budget, and meet all those design requirements to experiment with pipe size. And because it's the foundation of all your designs, it's not something you're likely to play with later. Refining pipe size by hand is millions, if not billions, of combinations, depending on the size of your model. Something essentially impossible, finding a needle in a haystack. But to computers is pretty trivial, since it can run all these different calculations and comparisons thousands of times per minute. Creating a design objective is what enables that computer to objectively compare those designs. And to get the ANS module running, all you really need is design objectives, design requirements, candidate sets, and a few other small things like which pipes you're sizing. That's all you really need to get the ANS module up and running. And that's about it. Hopefully you've learned a lot in the past hour. I'm glad you could spend your time here. Even if you don't take a look at the ANS module, maybe you're taking a second thought about how you're doing your pipe sizing and some of the marginal gains that you can give. If you have any questions at all about the ANS module, if you need a quote or anything like that, feel free to send me an email at nickbastine@aft.com. Or if you have any lingering questions, we'll try to figure them out together as well. If you have any ideas for future webinars, feel free to submit a topic to webinars@aft.com. And as always, we try to send out a recording of the webinar after these. So if you have coworkers who aren't able to make it live, we can send that out to them. Feel free to pass it around. But other than that, I hope this was a good use of your time. Thank you for spending your hour with me, and we look forward to having you attend future webinars. Thanks again.